Yet another way to do Markov chain Monte Carlo sampling is via what is called the Gibbs sampling. And I will write down the algorithm, and the algorithm is very simple. So let's say we have density over two variables, theta 1 and theta 2, conditional on the data. So everything we write is going to be conditional on the data. So for simplicity, I will just write probability of theta 1 and theta 2. I'll just keep this conditional on data everywhere to make notations a little bit easier to follow. And the Gibbs sample algorithm is very simple. So given that conditional probabilities are available, probability over theta 1 given theta 2, and probability over theta 2 given theta 1, if those are available, then we can write down the Gibbs sampler, and the Gibbs sampler is just you start by sampling theta 1. So you start with some theta 1 0 and theta 2 0, and at step G, you draw theta 1, and we're going to call it G, from the conditional distribution over theta 1, given theta 2 from the previous iteration, and then you draw the next part of your variable theta 2 G from the conditional distribution over theta 2 given the value of theta 1 G. That's it. So it's very simple. Of course, the caveat is that you want or you need the conditionals to be available, and also you need them to be positive. And the intuition why it works is given by this Clifford-Hammersley result. We will state it quickly here. Clifford. So the result is the following. So we will show the Clifford-Hammersley result for two variables. So let's say you have a joint density over two variables, theta 1 and theta 2. So we're just going to write down this joint density as a product of conditional, theta 2 and theta 1. And then the marginal over theta 2. Marginal over theta 1 here. And let's say we have another pair of variables that theta 1 prime and theta 2 prime, they come from the same density. So it's just a draw from the same density. And we're gonna introduce now theta 2 as a dummy variable, and we're gonna write down P of theta 2 prime given theta 1. And it's just a joint over theta 2 prime and theta 1 divided by the marginal over theta 1. So that basically tells us that P of theta 1 is just the ratio of the joint theta 2 prime and theta 1 divided by P of theta 2 prime given theta 1. And what you can do, you can take this one and just plug it in here. So essentially the goal is to write everything as conditionals. So we can demonstrate the Gibbs sample, and Gibbs sample everything is just conditional. And you can do the same for this pair of variables theta 1 prime and theta 2 prime. So if you write down the joint density theta 1 prime and theta 2 prime, again it's just a theta 1 prime given theta 2 times the marginal over theta 2 prime. And again, P of theta 2 prime using the base rule can be written as the joint theta 2 prime and theta 1 divided by P over theta 1 given theta 2 prime. Okay, and again, you can plug it in here. And now what we can do, we can write down the ratio of two joint densities. So we have theta 1 and theta 2 divided by theta 1 prime and theta 2 prime. And so from here we have P of theta 2 given theta 1. So it's this term here. And then if you look at this carefully, you'll see that in this ratio, this term and this term are the same. So they're going to cancel out. Okay. So then from the first joint over theta 1 and theta 2 at the bottom, we also will have P of theta 2 prime given theta 1. So it's this term here. And now from the second, we'll have, now we have to flip it, right? So this one was at the bottom, now it will be at the top. So it's P of theta 1 given theta 2 prime divided by P of theta 1 prime given theta 2. So it's this term here. All right. So what we've shown here is that if you have a ratio of two joint densities, you can characterize it completely using just the univariate conditionals. So everything you have on the right hand side is conditional, and it's one variable conditional on the other variable, and what you have on the left hand side is the joint density. So joint densities can be characterized by the sequence of conditionals. So that's the intuition behind the Gibbs sampler. Now let's talk about the convergence of the Gibbs sampler. So we'll write down what is called transition kernel. Transition kernel, so let's say you're in state theta, and you want to transition to the state theta prime. And again, we're going to continue using the case of two variables. By the way, it doesn't have to be two variables. It can be two blocks of variables, so you can do the block sampling. But let's pretend it's just two variables, and all of the derivations we do will be easily generalizable to a larger set of variables. So then this transition kernel, the joint density over those two states, is characterized by the joint densities. So it's P of theta 1 prime given theta 2, and P of theta 2 prime given theta 1 prime. So you go into the theta 1 prime given theta 2, and then you go into theta 2 prime given theta 1 prime. Okay, and so the conditional density is the only thing that we need. And then the stationary density for this transition kernel is defined as an integral. So it's so you take your transition kernel joint density over theta and theta prime, and you just integrate theta. So you integrate the initial state from it, and that's going to be stationary density over theta prime. Okay, and so we can write it down as, so that's integral over theta. So it's an integral over again theta, and here we have P of theta 1 prime given theta 2 times P of theta 2 given theta 1 prime d of theta. So it's prime here. So this part does not really depend on the theta, so that can come out of integral. So the only part here we have is this Q2 that depends on integral. And then we're going to do a little trick. So let me write down. So it's P of theta 2 prime given theta 1. And then we're going to integrate P of theta 1 prime given theta 2 d of theta. And then essentially it's double integral, right? So integral over theta 1 and integral over theta 2. And what we're going to do here, we can just we can multiply it by integral over theta 1 and theta 2, p of theta 1, theta 2, d theta. So this one just equals to 1 because that's a probability function. And so you can combine those two integrals, so you're just going to have a product of this density and this density under this double integral. And you can just simplify it, and it becomes so p of theta 2 prime and theta 1. And then you're going to have integral of p of theta 1 prime given theta 2, p of theta 2. Because this part here does not really depend on theta 1. And so if we just integrate theta 1 here, we'll have marginal over p of theta 2. So the integral only depends on p of theta 2 at the end. And now the p of theta 1 prime given theta 2 times p of theta 2 is just a joint over theta 1 prime and theta 2. And if you integrate theta 2 from the joint, you just get the marginal over theta 1 prime. So that just equals to p of theta 2 prime given theta 1. And then what you have here, theta 1 prime marginal over this. And of course, that's just a theta 1 prime, theta 2 prime. So that's a density over theta 1 and theta 2, exactly what we want. So we have our stationary density. So this type of transition, these kernels lead to stationary densities.